Hello everyone, I am Qi, a PhD student from Tongji University. Today it's my great honor to share our work on dataset distillation at CVPR. In this work, we propose the first universal dataset distillation framework for classification, detection, and segmentation tasks. First, let's review dataset distillation. What is DD task? It's a data optimization technique that condenses key information from large-scale datasets into a small size-set. This allows us to train model faster while maintaining performance comparable to using the original data. So the goals are clear. Reduce data size scale, accelerate model training, maintain model performance, and enhance generalization. Current dataset distillation research mostly focuses on image classification tasks, with less research on more complex detection and segmentation tasks. There are three mainstream methods like gradient matching, distribution matching, and training strategy matching. However, these methods are suited for small-scale, low-resolution data, and often yielding scientific images with limited quality. More recently, diffusion-based methods like minimax diffusion and Diffusion emerged to tackle large, high-resolution datasets. They leverage powerful generative capability to create high-quality scientific images that capture complex data distributions. A key limitation, however, is that these methods often require fitting the diffusion model on the large target datasets, which leads to additional time overhead. In this work, we propose one universal dataset distillation framework for multitasking, as illustrated in our UniDB pipeline. Our goal is to compress datasets for three visual tasks. For classification, we aim to preserve category information. For detection, we focus on bounding box coordinates, and for segmentation, we compress pixel level. The scientific images are randomly initialized from noise and generated by UniDB to match the target task labels. Here are visualizations of the three tasks generated by UniDB. Figure A shows the scientific image worth datasets. Figure B and C presents scientific VOC images generated by providing specific bounding box and mask information. UniDB perfectly handles both global size for classification and local target region size for detection and segmentation. Then, let's look at UniDB's detail structure. It's composed of two key stages. Stage 1, universal task knowledge mining. We extract task-specific information and contextual prompting from real datasets. Stage 2, universal task-driven diffusion. We leverage the mined knowledge to guide the diffusion model in generating task-specific scientific images. In stage 1, we train a task-specific practice model to extract key information from the original data. This is based on the consensus that a fully trained model can preserve essential dataset knowledge. Our TSP model is a standard model for its given task. For example, LessNet for classification or FastRCN for detection. Their task is its corresponding loss function, such as a simple loft-max noise for classification. Y is the labels, categories, bounding box, and picture level mask. Next is our task-aligned contextual prompting. Existing diffusion ED method often overlooks the role of rich natural language in generating diverse scientific data. Our solution uses a vision language model to extract natural language descriptions from original images, using a comprehensive caption library. For classification, prompts just describe object categories, like an image of green apple. For detection and segmentation, prompts include object relationships and object background interactions, providing richer contextual guidance. In stage 2, universal task-driven diffusion, our main idea is to guide the diffusion process at each step using our trained TSP model in stage 1. We adjust how noise is predicted by adding a component that guided by the task noise. This task noise directly aligns our TSP train. Since the TSP model trains on clean images, we first estimate a clean image with zero height. Then we use the TSP model to obtain a gradient that clearly guides the image adjustment. Lastly, we have a post-processing step, recursive-driven high-realism refinement. This helps fix issues from the diffusion model's redundancy by removing low-quality scientific images. First, use a trained TSP model to score each image. Then set a threshold to filter out low-quality images. Last, use the same TSP model to relabel the remaining images. Usually, we remove about 5% to 10% of the data in this step. We test UniD's performance on datasets for 3 tasks. On classification, we use ImageNet 1000 and 10 class subset. For detection, we use PaskVLC and MS Coco. For segmentation, we use PaskVLC. The blue line in the chart represents the performance of previous set of the art methods. As you can see, our UniDD significantly outperforms these SOTA methods across all 3 tasks. We compare UniDD with several existing methods, including MTT-based tails, decoupled-based SRE2L, RDED, diffusion-based D4M, and min-max diffusion. The bar chart clearly demonstrated the UniDD's performance improvement over this current method in the classification task. For detection and segmentation, since current dataset distillation has limited application in this task, so we benchmark our method against cross-site selection methods. Our results clearly show that UniDD always does better than cross-site selection methods for all compression data. When analyze distillation costs, we take a more comprehensive approach than previous work. Besides comparing distillation time, we also factor in the pre-processing time during the deployment phase. Overall, UniDD consistently shows the lowest overhead. Finally, let's look at more visualizations of our scientific images. This is the scientific dataset for the image group for image network. For images quark, it's all for classification tasks. And then with detection tasks on Wilson, on Coco, also on Coco, and segmentation tasks on Wilson. Thanks.